And the easiest way of doing this is just clean up all that stuff in the denominator, so that 1 over r. So the radial equation looks like this. So again, we have an unknown function, capital R, but it's only of one variable, lowercase r. And then again, you'll see why. Just again, with kind of like, you know, probably 200 years of hindsight, I guess, at this point. What do you suppose the solution to this is going to look like? Like what form of a thing? The constant helps a bit. But essentially what it's saying is what type of function multiplying it by a number is the same thing as taking 2 derivatives and multiplying it by r squared. So the variable squared.
Some kind of like polynomial.
Yes, so absolutely. So this has polynomial solutions, and in fact, it's got 2 of them. So if you crunch this out, you get that this has polynomial solutions. And honestly, that's the best way of solving differential equations. Stare at it for a second and say, what do you think this is? And then you get the answer. So this has polynomial solutions. And they could come in 2 forms. They could come with the L upstairs. So 1, 2 derivatives brings down an L, but because we multiply by r squared in between, we get back up to L plus 1. So that's where the L plus 1 comes from. And second type, I'll write it in, this is kind of the traditional electromagnetics textbook way of writing it, I guess. So these 2 things. Okay, these are 2 distinct solutions. We have a second order differential equation. So the general solution is just add them together. And if you don't believe me, you can just kind of plug these in and see that they work. So isn't separation of variables great? Like after all that work and that terrifying looking equation, like this is what you get, just a polynomial. It's wonderful. So any questions about that? Okay, I have a question. If I have a point charge, remember ultimately what this is this is part of an electromagnetic potential, or think about it like a voltage, in terms of how it should act and what your kind of physical intuition should be for it. This is the radial part. If I have a point charge, should I have A terms or B terms or both?
Point charge would be B terms.
Right, because you want to blow up at the origin. Exactly, yeah. Want to blow up at the origin and you want to go to 0 at infinity. If I have an infinite sheet of charged material, should I have A terms, B terms, or both?
Probably A terms. If it's an infinite sheet, you wouldn't want it to decay. Yeah, you wouldn't want it to like blow up at one point and then like kind of shrink pretty fast away from it.
Yep, perfect. So either of these are going to be useful in different physical scenarios. So in general, we can't throw one or the other away. Yeah, it seems weird to have an infinite potential, but sometimes we come up with infinite sheets of charge. So we can't just immediately discount one or the other of these terms. Great. Cool. So that was easy. Let's do the angular equation. And I'm going to be more suspicious about this because it has some funky sine and cosine terms. So the angular equation looks like this. Oops. And then doing the same thing where you just got rid of that 1 over theta and put stuff on the other side. So remember this constant, which again, now you know why people have chosen to call the constant L times L plus 1, after solving this for centuries. Looks like this. Less cool. So this actually, you got to kind of grind it out and do the calculus. So cosine theta, big theta dot sine theta, theta double prime. And then put this term on the same side. Okay, so I have a second order differential equation. I got capital theta double prime, I got a theta prime, and then I got a theta. So not the nicest thing ever. You can clean this up a little bit. And you can isolate the theta double prime term because I have 2 sines and 1 cosine. And then, so at this point, there are differential equation solvers like ODE solvers, and Wolfram Alpha, it'll probably give you the right answer. I'll give you the traditional way of solving this, which is a change of variables. And the reason to do this is because this is the kind of canonical, which is just a pretentious way of saying standard way of writing this particular famous differential equation. So if you do a change of variables and call x cosine of theta, then dx would be minus sine theta d theta. Then you can do this if you're a physicist. Right, so you can kind of think about this as little piece of x cancels. What this really does is it depends, you have to assume the thing that this is going to be acting on has, some sort of regularity properties, like it doesn't blow up anywhere. But for us, totally fine. But because we've told ourselves we've defined x as cosine theta, we know what dx d theta is. Dx d theta is minus sine theta. Okay, and now what I'm going to do is, to avoid confusion, we're going to change variables. We used to have theta of theta. I'm just going to call it y of x after the change of variables. And again, this is the so-called canonical form. Like this is what you'll find in a differential equations textbook. So once you do this, and this will be the thing that you go through in full detail as part of the homework. So this will not be half a page. So doing the separating the variables and going through all of the work for the spherical polar Laplacian, you get this. So we'll give this a name. So this is fine. So this is an ordinary second order differential equation. This is the ordinary second order differential equation that you could totally look up, find an integrating factor for. Standard techniques from DiffEq would solve this. I'm going to assume that, it's been up there, but the stuff in the video on Sturm-Liouville theory is like really abstract. What I want you guys to take from it is that ultimately this can be, we used L already today. This can be expressed as a differential operator acting on an unknown function y equals 0. Trust me, it can. The way that you can kind of analogize it is we have an analog, an infinite dimensional analog of matrix acting on vector equals 0. There's a whole suite of techniques to solve this. Essentially, it's an eigenvalue problem, right? In fact, if you really look at this, this kind of looks like an eigenvalue problem where this is the eigenvalue, L times L plus 1. And if you solve an eigenvalue problem, you get a bunch of eigenvectors, and the eigenvectors have great properties, like they're orthogonal to each other, they can form a basis. Anytime you solve an eigenvalue problem, you basically get a natural basis of the functions, or natural basis that makes the most sense of the problem. So if you find the eigenvectors of an inertia tensor, what you get are the three principal axes about which it's easiest to flip the thing. So in the case of like a tennis racket, you'll get one of the eigenvectors describes down the tennis racket, the other one describes perpendicular to the tennis racket, and the last one describes the flipping that you never see a tennis player do, which is the one that's really hard to draw around there. So you'll see tennis players spin it. You'll see tennis players flip the thing up and down, like this way, I guess, is the best way I can draw it. You never see them flip it the way that, like if you were to flip a pancake, but the pan went with it, that's the middle axis, which is unstable. So, and those would be the eigenvectors of the inertia tensor. Slight digression. So we have a differential operator acting on an unknown function. So it's kind of like an eigenvalue problem. In the middle of the 19th century, Sturm and Liouville said that, well, in the same way that the eigenvectors that come out of an eigenvalue problem form a basis, the eigenfunctions that come out of a differential version of this, they also form a basis in the same way that the sines and cosines of the Fourier series do, which is to say they're complete. You can represent any function you want with them. All the information is in there. Turns out we've already got part of it. You can express anything with polynomials. That's essentially Taylor's theorem. That was our radial equation. We're going to get a more exotic one. But before I write down the solutions, I'll just say this does have a Sturm-Liouville form. And again, you can think about that like, oops, eigenvalue, little stupid bars in the way. Eigenvalue, eigenvector, matrix. So kind of an analogy to this. So basically Sturm and Liouville say that y's will form a basis through which we can represent any function at all. So this is great. This means that anything that you paint on the charge distribution, the answers will be able to represent that. Again, sort of a digression. So the other thing it says that the second you find one of these solutions, you can use it to find the other solutions. And we'll do that slightly laboriously, but I'll just say like, let's find one solution and then use it to generate the rest. So So every one of these L's that we pick, it's going to correspond to a unique function. You can just kind of see that by looking at the differential equation. Each L. But it's also going to be able to generate a basis. So we will remind ourselves of one thing. So we changed variables from theta to x through x is cosine theta. This means that x is constrained to be within -1 and 1. Okay. So let's start by choosing L equals 0. It's kind of a subtle question as to why L equals 0. Because we're taking derivatives of sines and cosines, essentially, the somewhat cheeky answer is, look, I'll write down L equals 0, we'll generate a function, and then you can just dump it back into the differential equation and show that it works. So we'll start with L equals 0. So looking back at the differential equation, I have 1 minus x squared, y double prime, minus 2x prime, LL plus 1, which is 0 times 1, which is 0. Y equals 0. So 1 minus x squared y double prime equals 2xy prime. What is it that solves this? So just an ordinary differential equation, basically dot, 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 same argument that we made with the axial equation. In fact, we're taking two derivatives multiplying by x squared. We're taking one derivative multiplying by x. This has got to be a polynomial. It turns out that it equals constant. And what we're going to do is we're going to subscript this by the value of L. So YL is equal to a constant. And in fact, we're going to choose it to be equal to 1 by convention. Okay. So trivially, this is true, right? So I take the derivative of a constant once and twice, and I get this. So great solution. It'll work for all of these Sturm-Liouville problems that we'll talk about in this class at least. So for L equals 0, I would always try a constant. Okay, so we have two options, to be honest. We could just plug in this thing for L equals 1, and then we would have a 2y term over there. But there's an alternative. The alternative to generate new solutions is essentially I know I misspell one of these always, Gram-Schmidt, yeah. S-C-H-M-I-D-T, okay. Do you guys know what the Gram-Schmidt process is for making bases? Okay. So let's say that I have a unit vector, we'll call it E1. And then let's say I have another vector that doesn't fall along E1, but is not so it's not parallel to E1. I could totally use this to make a second basis vector, right? As long as it's not E1, it's got some part of it that is perpendicular to E1. All I have to do is I've got to remove the part of this that's parallel to E1. So I know how to do that. I just do v2 dot E1. Problem is that's too long. So I do that. This is the part of V2 that lies along E1. So I just remove that from V2. And then that itself is too long. So then I divide it by the whole thing. Okay, geometrically, this should make sense. the equation itself looks really gross. What I'll end up with is this. I'll end up with the piece of this that doesn't lie along E1. In 2D, it's really easy to draw. So the Gram-Schmidt procedure is subtract off the part you already have, essentially. So I think I asked you guys to put something once into the Sturm-Liouville format, just to kind of get a sense of what it is. But the whole point of talking about it is that if we can guarantee that we have a basis, once you have one solution, you can generate a second solution by just removing the first part. So the idea is this. This all sounds probably like super crazy, but this is where we're going, is look at our differential equation. We're pretty sure that our solutions are polynomials, right? This is the most general polynomial I can write down. Okay, we've already taken care of this term. We know our next term is going to be perpendicular to it. What do you guys want to try? What would be the nicest polynomial term that you might hope would solve this if we're lucky? And remember, pick something. I throw it into the differential equation. If it works, and we keep it, right? All of this is just kind of like guiding some guesses. Okay, can't try a constant because we already have a constant. What's the next term that you guys want to try? Please
Maybe
don't
y
make work
equals
for me.
x. Just
Great.
very
Let's
kind
try y equals,
polynomial.
yes. Yeah, let's just try y equals x and see what happens. And what's the term that you guys want to try after that? Okay, remember that if it doesn't work, we might have to subtract off a piece. But honestly, it's just, look, we've already got this part covered. What's the next thing we can try? So let's try, this would be y1 of x equals x, technically is proportional to x. And then we want to dump it into the following differential equation. Equals 1 times 1 plus 1 is 2. So put that in there, and then, okay, we have 1 minus x squared, 2 derivatives of x is 0, so that's gone. 1 derivative of x is 1, so minus 2 times x is 2 times x. We're so close. So what do we need to do? We got to maybe put a constant in front of this, right? So a constant equal to minus 1 might do it, but so something proportional to x works. And just to show that this satisfies the other thing that we care about, so that y naught is orthogonal to y1. So this would be true even if we have a minus 1 in front of it, any sort of constant. The integral of this vanishes. So the overlap of y naught and y1 is equal to 0. So this is kind of the functiony way of saying that y1 dot, in some sense, y naught is 0. So their inner product vanishes. So this is the idea of essentially thinking about the solutions of a certain class of differential equations as basis functions. And you know properties of basis functions, namely they're perpendicular to each other. So you can see that with 1 and x, the first two we found. And you know, if you're really hard up, you can actually generate one from another, which is what we have to do for L equals 2. So right now we've got this. Let me put up a little table. So we have L and Y L of X. So L of 0 is 1 by sort of convention. Y1 is X, again, chosen by convention. And then 2, so 2 needs to be at least include a second order polynomial. And because it's a little bit more interesting, there are more terms, I'll show you how the sort of Gram-Schmidt idea would work. So for L equals 2, and I kind of don't trust this stuff, maybe because I've just started working with these ideas. I'll say that this needs to be something that looks like ax squared plus bx plus c. And then what I'll see is, I worked a little bit too hard, and maybe, I could have thrown away some of these terms right at the outset. Okay, so we need a second order solution, and we need to be orthogonal to both y0 of x and y1 of x. So this is really the Gram-Schmidt process. This is taking the solutions that we have, taking something that is linearly independent from that. You cannot make this from a linear combination of those, and then projecting off the parts that we already know correspond to solutions. In the same way that if I gave you a vector that was not linearly independent to the two other vectors, you could generate a third basis vector from it. Okay, so the way that we would do that is we overlap y2, our trial function, with y1 dx over the specified interval. And this better be equal to 0. So that's ax squared plus bx plus c times x equals 0. All the odd terms go away. We're just left with even terms. So this would tell me that, write it all out once. So we got a fourth over x to the fourth. So because this needs to be 0, the a and the c terms vanish naturally, the b term doesn't, because we got the minus minus 1. So this thing implies that b needs to be equal to 0. Okay, and what also needs to be true is this thing can't have any overlap with y0 dx. So these are conditions that we're enforcing to be true, because we're trying to generate, these guys, Gram and Schmidt, told us that we're going to make a basis. Our basis needs to be complete. So we need to be able to represent everything. We're enforcing the condition that each new solution needs to be linearly independent from the last. So we'll do this. I'll just dot this. And then what you get is, we already showed that b is 0, so I'll get rid of the b. And then this, if you integrate out, you get the condition that a equals minus a over 3 equals c. Okay. So that would mean that y2 of x is equal to 3x minus 1. And just by convention, in the same way that there's kind of a 1 chosen to be there, there's a 1/2 chosen to be here. So this is 1/2 3x minus 1. You can keep doing this. So again, there are two ways of doing this. One is for every single L, you can write down the differential equation, try to solve it with standard techniques like integrating factors. I'm just describing an alternative method based on the idea that these are basis vectors. Okay, so there's another solution that you could get through either of those techniques. It's going to be I think I have a missing squared. There's totally a missing squared here, sorry. And then 5x cubed minus x. Yeah, that's nice now. And then I'll just write the fourth term. I don't even know if I can fit this in here. I think it's 1/8. Right. Okay, these things collectively, PL of x, are called the Legendre polynomials. And the differential equation that we were solving to get them, not directly by solving it, but by using some of the ideas of Gram and Schmidt and the theory of orthogonal functions, is called the Legendre equation. Okay, and what you can do is you can show that PL of x, let me see if I can ask this question like 500 times during the course of the quarter. PL of x, PK of x, in this case, integrated from -1 to 1. What does that equal? So in this case, L and K are just integers.
If they're all mutually orthogonal, then it should be 0.
Yep, when L and K are not equal. And then when L does equal K, it turns out that something happens. So there's some constant, unfortunately, to ruin everything. But this is proportional to the Dirac delta function. Right. So that, again, is what a basis means. So we have, in this case, a basis of polynomials. And again, the assurance that we have from these guys is that certain types of differential equations will guarantee you to have the solution. Okay, I will point out that there is a second set of solutions that turn out to be like really unphysical for us. There's like a natural log of a tangent, but we'll talk about that when we kind of go back into discussing the thing that we wanted to solve in the first place. So remember, we did a change of variables. And what we really wanted to do was solve some axial equation, which was a function of theta. So what does this have to do with that? Okay, just remember, this is what we wanted to do all the way back at the beginning. We had a solution that, or an equation that looked like this. And we didn't do anything to the L, but we did change variables from theta to x. So we got into this format. Through a change of variables, x is cosine of theta. So this is what we actually ended up doing, is that our solutions of theta, what we wanted in the first place, are sums of Legendre polynomials of cosine of theta. And L could be anything in between 0 and infinity. And these things could have their own personal coefficients, which I didn't leave room for. Just give me 1 second. So call this C of n, C of L, P of L cosine of theta. So we really kind of got lucky with the radial equation, and the axial equation is kind of gross. And we now have the entire solution of the entire thing. So in this sense, we're done. So that's actually really worth celebrating. So finally, so for an azimuthally symmetric electrostatic potential, we can write our solutions like this. Remember, the L is the same for both the radial and the axial equation. So on the A's and the B's, the subscript just says like, which one are you? So that's the radial piece. The axial piece would have its own coefficients if you solved it by itself, but because you're multiplying the C by all of these terms, you can just kind of consolidate them and make your life a little bit easier. So you can absorb the C's into the A's and B's if you'd like. So this is the whole thing. So this is the theta of theta and the R of R. So this is what we called R of R, and this is what we called theta of theta. Okay. And these are Legendre polynomials with cosine instead of x. So it's literally take that table, replace x with cosine. Okay. Radial equation, nice. Axial equation, it's actually not that bad. It's just maybe this stuff's a little bit new. And in advanced E&M, you'll basically completely resolve this problem. So it's one of those ones that like you need to see it 2 full times before everything really starts sticking. So what I want to add is that our program for a lot of this stuff is going to be somebody writes down a differential equation that's important for physics. We're going to snoop around and say like, well, is it in the Sturm-Liouville form? If so, the solutions that it generates are going to be orthogonal and they're going to be complete. And we hope they're complete because that means that they can represent anything. Okay. So that is all the rarefied theory. Any questions about that before we actually show how to do this and solve an actual problem?